Hello guys, welcome back. So today we will start a new chapter on principal component analysis. And I think we can spend one lecture on this. And for the next Thursday, we can talk about some clustering algorithms with primary focus on k-means, right? Because principal component analysis (PCA) and k-means clustering are two methods that are often used in combination as a basic unsupervised way to investigate patterns in data in general. Okay, so I think this is the first time that we talk about some non-parametric methods in this course, because all the machine learning models so far we have talked about, from basic logistic regression models to neural network to deep neural network, convolutional and recurrent neural networks. Basically, all models are parametric, which means they have parameters to be learned, to be trained using gradients method, like gradient descent. But from this lecture on, we're going to talk about, at least we will spend this week on PCA and clustering, which is basically non-parametric, that we don't actually require models require parameters to be learned from data. We actually also don't require the actual labels on the data, because we're not studying the map between the features and the labels, but rather we are looking at the distribution of the data itself. We want to find some patterns without human supervision, without supervised, without labeled data. All right, so let's talk about PCA today. Okay, first we'll look at what is PCA and what exactly we need. Why do we need a PCA? And then we'll look at a detailed methods of how PCA is conducted, and then we can look at several applications of PCA. So what is PCA? And we can define it as a way to reduce dimensionalities, or to reduce dimensions in data, that it can actually remove redundant dimensions. Say if you have a data set that is of very high dimensionality, you have way more features than you expected, then you can use such a technique to reduce the dimensionality to the number of dimensions of your desire, or of your interest. Okay, so that the most important dimensions can be kept, while those that are not relevant, not that informative, or not that irrelevant will be removed. Okay. And it's also an effective way to visualize the data. Say, because we cannot perceptually watch a data set, like perceptually see a data set that is of more than 3 dimensions, right? We cannot like visually see a 4-dimensional data, not to mention those data that is of even higher dimensionalities, right? So such a technique will allow us to see how those data points cluster in space, for example, how they, or at least how they distribute in space in a 2-dimension space or 3-dimension space, for example, right? So that actually applies to quite a broad range of data. Like the word embeddings that we have talked so far is a very high dimension data sets. We usually speak of like, we can usually use like a 100 dimension or 300 dimension, which is a very large number, right? It's basically a necessity to reduce the before we can see them directly, see their distribution directly. And for image data, for bioinformatics data, it's also a very common scenarios. Okay, so we will start with a concrete example, but it's a more of a toy data sets rather than realistic data sets to go through some basic concepts and the basic procedures necessary for PCA. And through that, we hopefully we should also understand better why PCA is needed in such cases. All right, so let's look at our example here. We have a bird data set, right? We have, so it's kind of a transpose data set because, well, it's if you're used to put each data instance as a column, then it's the way that it should be used to with, like the first column is a data set. It's a data points, which is the first bird in the birds data set. And we have, so far we have shown 3 features, right? But the dots here show there could be more than that features. We have weight, wingspan, and length. And for the first bird, the weight is 10, and the wingspan is 6, and the length is in 7 inches or whatever other units it is using, right? And for second bird, it has its own feature, right? Third bird. So it's okay, right? If you have only 3 features, and it's possible, it's doable that we plot those data points in the chart. It can be a scatter plots or whatever other type of plots that you can explore with. But the thing with the dimensionality is that there could be more than 3 features, right? And in those cases, we need to figure out a way to reduce the dimensions, and so that the data can be visualized. And the second question is that we actually don't know how those features are correlated. That is a critical question because, sometimes introducing new features can be problematic, or it will not bring in as much information as you expect. So, for example, the wingspan here is basically kind of a measurement that is related to the length of a bird, right? And it should also be positively correlated with the weight, right? Basically speaking, you have a longer wingspan, the bird should be heavier, right? So all those features, they are not totally unrelated, but they're more or less correlated with each other, right? So in this case, when we have multiple features that are correlated, then it is necessary to ask questions that what are the most informative or what are the most useful or significant features to describe the data, right? Because when we use weights, it actually, part of the size information is also included in weight, right? And a part of the wingspan and length, for example, they are just the length, the size in different directions, right? So those measures needs to be carefully designed and selected in order to describe the data better. Okay, so we need to keep that in mind, that the features we get in the raw data sets are not necessarily the best ones to describe data sets. Okay, there could be more meaningful ways to construct some new features out of the existing ones. Okay, and that is also a common outcome that PCA can help achieve. Oops, okay. So now speaking of how many dimensions we need to keep, right? That is actually really at the core of this our discussion here. Like we have maybe 4 features, and how do we determine what are the most important features? Or we can say, how do we select features among these features, among those existing features? Or more than that, how do we construct new features that are better than the old features? So we say better than we are actually comparing them, right? So there must be some standards, some threshold to use to compare, to determine how good a dimension is, how good, what are the good dimensions to keep, right? So basically speaking, the general principle is that if we have a dimension along which that data have very high resolution, which means the data points along that dimension actually spread out a lot. Okay, they are scattered basically. Then we say that dimension is very informative in terms of describing the data, right? So for example, if we have 2 dimensions, if we look out to the scatter plot of the data, for example, and the data looks like this way, and assume that's the raw data, right? And assume that the x-axis is the length, right? And y could be the weight, for example. And you see that the distribution of the scatter plots is very narrow, okay? So if we compare these 2 dimensions, we have a weight and a length, right? So if we look at like how spread out these data points are there along these 2 dimensions, then it looks to us that if we look at the horizontal direction, it has a larger scope, right? It has a larger range. It's spread out within a much broader range along this length, which means there's a higher diversity in terms of data points along that length. Okay, and also that we can say that the length tells a lot of the difference between those data points, and the length is a very informative feature as compared to the weight. So because if you look at this direction, the range of all data points along this weight is actually a very narrow one, and it's really hard to distinguish, to tell these data points apart in terms of weight alone. Okay, so in this particular case, then probably length is the one. I mean, very likely that length is the feature that we want to keep as opposed to weight. Okay. So this is an extreme example of how good those features are in terms of how spread out data points are along those features. And this is basically the principle that we will use to carry out principal component analysis. All right. Okay, so let's see. What essentially PCA is doing is that it will find a new set of dimensions, and such that all these dimensions, they are orthogonal, or they are kind of perpendicular towards each other. So it basically guarantees independency. That means any of those 2 dimensions returned by the PCA, they are not like correlated with each other, but they are rather independent features. Okay, and this connects to the last point that I didn't mention, which is that we want those features to be independent. So if a good dimensions, so if there are some good dimensions to describe data, we want them to be as independent as possible, right? Otherwise, there's the so-called collinearity issue or the correlation issue. That's when we talk about wingspan, we actually also it's also partially about the weight. So that makes the interpretation of the data not that it makes the interpretation more ambiguous. Okay. So that's why we want the PCA to, we want to use PCA to make sure that the dimensions, the resulted dimensions are orthogonal. And more importantly, all those dimensions returned by PCA, they are ranked according to the variance of data along them. Okay, because we mentioned that in the previous example that we draw on the screen is that along the horizontal length dimension, there's larger variance, right, as compared to the vertical weight dimension. So if we want to rank these two dimensions, then we will basically rank the length higher, because along that length dimension, the variance data is higher, right? Which means it explains more about the data compared to the other one. Okay. All right. So now let's step into the details of how PCA can be conducted along a simple data set. Okay. So let's simply start from a 2D dimension space, so that it's easier for illustration. Okay. But this is a very extreme example, because usually speaking, in actual practices, we don't apply PCA a lot to that dimensional data sets, right? But that is not for sure. You can always apply it for exploration, for interpretation, and so on. Okay, say we have a two-dimensional data sets that each point, each bird is described by a weight and wingspan. So the weight is x1 is the first feature, and x2 is the wings, is a wingspan, which is the second feature. And we have 6 data points. And if we plot the raw data points, right, with the raw features, without any normalization, without anything fancy processing, then we can basically look at, it looks like that way, right? It looks like a pretty linear relationship, right? If you imagine there could be some linear models fit to describe the model, right? But that is not our focus today, right? So with the raw data points, what we need to do first is that we compute the mean values for each feature. For the weight, we basically compute the mean values by summing up all those weights, 10 plus 11, plus 8, plus 3, plus 2, plus 1, and then divided by 2, which gives us a mean value here. And the estimated variance or standard deviation can also be computed, which is basically the summation of each data points minus the mean value raised to the power of 2, that is a square, right? And divided by n minus 1. That is a unbiased estimation for the standard deviation, right? So we do that for each of these 2 features, right? That is the basis for our next step, right? Because you may guess that what we want to do next, right? So it is to normalize the data, right? That's a usual practice. We just normalize data by subtracting the mean values to each data points, okay? So the mean values for the weights is mu1, it's extracted, and the mu2, which is the mean values for wingspan, is also extracted from the data sets, and then normalized by the, I should use a different color, right? It's also divided by the standard deviations of the weights and the standard deviations for the wingspan. I think this is a pretty something we are pretty familiar with, right? So by doing this, we actually centered move the data points to the center, right? And then scaled the 2 dimensions so that they are all along the same same scale, right? So they are pretty close numbers that are close to 0 with some variance, right? With standard deviations equal to 1. All right. So from this step on, we can start thinking about the question of our goal is to find a dimension that best describes the data, right? So using the standard we have, which is to find a dimension that's find a dimension along which that the data points have as much variance as possible. Okay, so we want to basically find a dimension that if we look at how data varies along that direction, then we can measure that degree of variance, and we want to find an angle, find a dimension that the variance is maximized. Okay, and we want to avoid the extreme cases that the data are scattered around a very narrow region, as we have shown in the previous drawing. Okay. All right. So that is our goal. Okay. So let's see what we can do. Okay. So let's think about the problem into find the direction. We want to find the direction and for all the data points to project onto. Okay. And after the data points are projected to that direction, we can measure the relative variance of the projected data points. So we want to maximize that measured variance. So for example, we just randomly draw a dashed line, which can be some candidate dimension. Okay, so if that is, so another something I didn't mention is that the notation. Okay, so there's a x tilde and the x2 tilde, which is the normalized data. Okay, so there's just a curve, a wave, right? It's still a curly hats for on top of each letter here. Okay, so we have the normalized data and we want to find a direction. It can be a line or a plane, so that onto which the data, all the raw data points can be projected onto, right? And say if we have such a candidate dimension, right, in the dashed line, what we can do is to project each data point onto that dimension. So we can use the distance between the 0 points and the projected points. So these points, the location of this circle is where the original data points projected onto the candidate dimension, right? So that is where the projection is. So the distance between the projected points and the 0 points is the distance of the projection. Okay, so let's call that D1 because it's associated with the original data points P1. Okay, so we do that for all the data points. For P2, we will have a second distance, D2, for all of those distances. So we can simply use the sum of squares of those projections to measure the total variance along this candidate dimension. Okay, right? No matter how the candidate dimension change, we can always get the projection and then measure the distance of each projection and sum up the sum of squares. And that sum of squares is the quantity we want to maximize, right? Because we want as much variance as possible, right? We want to maximize this quantity, okay? So let's look at several different options. We can choose a candidate in this way, right? Or it can be this way, or this way, right? With different angles, the dimensions, the projections will be different, right? So for example, let's say this is the direction that maximize the sum of squares, right? The sum of squares of variance distances, right? Then we can call it this direction in this direction indicated by the red dashed line is the principal, the so-called principal component 1, or the first principal components. We can write it down, use PC1 for short, okay? So that direction is the PC1, okay? And if we look at the projections onto PC1, that sum of squares is actually maximized. So because that PC1 is it's a direction, so it can be described by a vector, right? So in this case, the data is two-dimensional data. So we can use a two-dimensional vector to describe the direction of PC1, okay? So basically, we can use a unit vector, which has unit length to denote the direction of PC1. In this case, for example, it's this vector, 0.94 and 0.34. Okay, that is the direction of PC1, for example, right? And this actually, this new direction is the linear combination of x1 tilde and x2. So that means the U1, the meaning of U1 is that it takes 94% maybe of the x1 plus 34% of x2 tilde, right? So that is how these numbers, or what actually means to the original features, right? So that is a linear combination, which is our PC1, right? So given PC1, we can easily find the second principal components. Okay, because the second principal component should be orthogonal or perpendicular to the first one, because we want the two dimensions to be independent of each other. So the red direction, the green dashed line direction is our PC2, right? So if we look at the projections onto the PC2, the total variance would be much smaller than the PC1, okay? And it's perpendicular to PC1, and it's also a unit vector. In this case, this unit vector U2 is perpendicular to U1, right? If we compute the dot product between U1 and U2, actually we will find 0, okay? That is, in this case, how this PC1 and PC2 looks like, okay? So the projection also, as we said, the projections on PC1 has a larger variance. The sum of squares on PC1 is greater than the sum of squares on PC2, okay? So with these two principal components, we can actually switch to a different angle to look at the data points, right? Because we have U1 and U2 now, we can basically use these two vectors as the new way to describe the data. Okay, they can be the new coordinates here, right? We can basically rotate the data to the new basis, okay? We have two basic vectors, which is U1 and U2. So we can use this U1 and U2 to describe the data, okay? So now we represent the data, use our principal components. So compared to our traditional, the old view of the data, it's kind of rotated, right? And the advantage of it is that the PC1s, the new axis and y axis, the new say features, they actually describe more variance than those raw features, right? The raw weight, the raw wings, they don't explain that variance as those PC1s. Say if you compute the projections of your data points onto the weights, and you get some sum of squares on weights, right? that will not be as great as the projections on the PC1, right? So in that, speaking from that perspective, the PC1 is a better feature because it describes describes more variance than the original features. Okay. All right. And here comes the practical problem. How do we find those PC1 and PC2? How do we find these two unit length vectors, U1 and U2? Right. So that is the next question we're gonna look at. Okay. So it's a problem of finding where the problem of finding a vector, right? We can denote the principal components as a unit length vector U, which is to be